We are now looking at section 3.6, which is about rational functions. Like other functions, we will define the domain or find out the domain, find out the intercepts, and eventually our goal is to get to graphing the rational function and without the use of a calculator. So that's our goal. And so what is a rational function? We can actually compare it to a rational number. How do we define a rational number? We say it is a number of the form p over q, like a fraction where p and q are integers. So they can be integers, they cannot be irrational numbers or rational numbers. Like we cannot have like 2 over 3 divided by 3 over 5. This is not a rational number. We first have to simplify it. If we can get it in the form an integer over an integer, then that way we can get it into the rational number form. But in this way form, it is not called a rational number. In this, and then condition on q is that q is not equal to 0. Q cannot be 0 because 0, we cannot have it in the denominator. In the same way, we say that the rational function is a fraction of functions, or is a fraction between functions. But what are the condition on those functions? Those functions, each of them should be a polynomial. We say a rational function is of the form p of x divided by q of x, so a function p of x divided by a function q of x, where q of x cannot be 0, so it is not equal to 0. And but that doesn't mean that we will always have a function which is not 0. We could have a function which is 0 at some points, but the thing is those points will not be in the domain of the function. And so another condition I think should be that q of x, the degree of q of x should be a greater than or equal to 1. The reason is that if you have a polynomial 2x squared plus 7x minus 5, and we are dividing it by, let's say, 5, then 5 is a polynomial but of degree 0. Okay? But we can easily now convert this to 2 over 5x squared plus 7 over 5x minus 1. Now this is a polynomial. So this is no more a rational function, because in the rational function we must have a polynomial of degree 1 or more. Okay, so let us look at this function we have seen before, which is 1 over x, and this is called the reciprocal function, if you recall from before. And we notice that typically, and we like state it without even sometimes knowing what we are talking about, but we say, okay, why is it x is a asymptote to the function? What kind of asymptote? Because y-axis is a vertical line, so we say y-axis is a vertical asymptote of the function. But what it means in terms of the function values, that's what we are going to look at. And then also we say horizontal asymptote. We have the x-axis is a horizontal asymptote of the function. So we will say equation. So we will say vertical asymptote is x is equal to 0. We will not say vertical. Sometimes students say VA is equal to 0. That is not correct. And I often take off 1 point for, if someone wrote that equation, because you are supposed to write the equation of the VA, not saying that VA is, we are not talking about value of VA. If VA was something whose value we were finding, then we could say VA is equal to 0. But we are not finding the value, we are finding the equation of the VA, equation of the vertical asymptote. The vertical line always has an equation, x equal to a number. So how do we figure out? Well, x is equal to whatever the number is where the function is not defined. That is where the vertical asymptote will be. So So what happens actually to vertical? Why do we call a line vertical asymptote? The reason is because if this happens, if this situation happens, that as we get closer and closer to the value of the vertical asymptote, in this case 0, right? As we approach 0, we can approach 0. Notice here we can approach 0 from the right. So by taking on these values, I can get here, or by taking on these values from here. Okay. So for example, one is too far away from 0. We want to get closer and closer to 0. So a value from the right side. What does it mean from the right side? In this case, it means the positive value. A positive value that is very, very small. So we express it like this: as x approaches 0 plus. So the plus sign up there. So we say from the right. So as x approaches 0 from the right. So we write it like this: x arrow, whatever your vertical asymptote is, that number raised to plus sign. That means approaching that number, that x value from right. So what does that mean? It means pick a very small x value, for example, but it should be a positive x value. So for example, 0 0 0 0 0 0 1. I have 5 zeros, and then sixth position is with the more. I pushed more than necessary. Okay, so we have again it will work with this as well, whatever. So but if we have this x is equal to this value, then what will be the y? Y will be 1 over that value, and if you want to write it in the scientific notation, this will be, count the decimal places, 1 2 3 4 5 6 7, so it will be -7, 10 to the -7. And when I put it over here, this becomes, by the exponent rule, this becomes 10 to the 7. And what is 10 to the 7? It will be 1 and then 7 zeros in front. So can you see how big this number is? It's a huge number. So what is happening, as x goes to 0 from the right, y goes to, so here we notice that as x goes to 0 from the right, y goes to infinity. Y is becoming unbounded. It's growing and growing and growing. Now we do the same thing from the we approach 0 from the left, and we denote it by x approaches 0 minus raised to the negative sign, which means x approaches 0 from the left. So now I am going to take a very small negative value, so we can take something similar but with a negative sign, 0 0 0 0 1. Okay, let's do this. So what will be the one y value? Y will be 1 over this value, negative 0.0000. I have 4 zeros and 1. Okay, what is this? If you have a calculator, or if you know, this will be negative 5 zeros. Okay, so which is a very big negative value. So what can we say here? That as x approaches 0 negative from the negative side, or from the left, y approaches negative infinity. Y is becoming a very large negative number. So this tells you that the function will be, if we are coming from right to our asymptote, this is the behavior that you will see, that the y values are coming from a very big high number to smaller and smaller and smaller y values. And on the left, so you notice that when we are close to 0 from the left, the y values are decreasing still, and becoming in negative, bigger and bigger negative values. So this is the behavior we notice around the vertical asymptote. So this is not the only case. Sometimes in some cases you can have the situation that if this is your vertical asymptote, you can see a behavior like this goes like this and this goes like that. So from we can say in this case, as x approaches 0, x approaches 0 from the right, y is approaching infinity, and as x approaches 0 from the left, y is still approaching infinity. Okay, so you can see if y is growing up and up and up. So this is what we call the behavior around the vertical asymptote. And we could have them flipped, like both ways. It could go down, or it could be the other case. So there could be 4 cases. We could have a situation like this around the vertical axis, or we can have a situation like this around a vertical axis that we are just seeing. And another one is that we could have this situation around the vertical axis, or the fourth one is that we could have so not always your x-axis is going to be the horizontal asymptote. So whatever horizontal asymptote is, so for example the x-axis was here and the function is the HA is here, so the function could behave like that. Okay, so what about the horizontal asymptote? So for the horizontal asymptote, we are basically trying to see what happens when our function gets closer and closer to the x-axis. What is happening? Okay, so we are saying when x gets bigger and bigger, where is the y value going? So in our case, in this example, we notice that as x becomes bigger and bigger, we are going to get closer and closer to y is equal to 0, getting closer and closer to 0. So the difference is now here, in the case of vertical asymptote, we are letting x go to a number from left or right, and then we notice the behavior of y is infinity or minus infinity. In the case of the horizontal asymptotes, we look for when x goes to infinity and negative infinity, where is y going? So y will be going to a number, and that number is the horizontal axis. So that's what we can write over here. So this is saying as x goes to plus infinity, y goes to, so we notice from the graph that y is getting closer and closer to 0. Then you can also do that by plugging in values. So if you say let x be like 10 to the 7, okay, which is a big number, means it will have 7 zeros in front of 1. 1, 2, 3, 4, 5, 6, and then 7. Then y will be, remember, is 1 over x. So y is going to be 1 over this huge number. So where am I going? Almost about 0. So 10 to the 7, so this will give you almost 0. So as x approaches infinity, y is approaching 0, which is what we have here. Now what if x has a big negative value? So let x be negative 10 to the 7, then what will be the y value? Y will be negative 1 over negative 10 to the 7, or negative 10 to the negative 7, which is going to be a huge 1 divided by a huge number, which is almost 0, but not exactly 0. So we can keep the negative sign, because remember, if you have the 0 value, then you don't have the sign with it, because 0 is not a positive number, neither is it a negative number. But we are getting there, we are not getting equal to 0. So that's why we can have the negative number. So this shows us that as x goes to negative infinity, y goes to 0 still. Okay, although we have a negative value, but still it is going approaching 0, but through the negative values. That's what it is says. And that makes sense because over here on the left side, our function values are below the x-axis, so they are negative values. So this is how we think about the vertical and the horizontal asymptotes, or this is how the concept of asymptotes should be understood. And so we have talked about vertical and horizontal asymptotes. There are sometimes we have slant asymptotes. So we are not going to discuss those over here, but that is again a concept that maybe at some time you will learn. Okay, now I mentioned up there what rational function is. So based on that information, can you guys figure this out? So I'll give you a few minutes to think about it. Which function is rational, which is not rational, and if you can give the reason why it is not rational. Okay, I think you must have sort out the functions which are rational functions, and looking at the definition, what does the definition say? That it will look like a fraction, right? But the top and the bottom both should be polynomials. So if we look at this first one, you can see a polynomial of degree 1 here, polynomial of degree 1 here. So yes, this is a rational function. Okay, so we can say so this is a rational function. What about the second? Well, we have a polynomial at the bottom, but on the top, which function is this? Now you guys should know the names of these functions. So this function is a radical function. This is not a polynomial. So not a poly. So not a rational function. What about g of x? It is 2 over x squared plus 2. Well, if you again recall, when I gave you the definition of the rational function, I put a restriction on the degree of q of x, but I didn't say anything about p. So here we have the p is of degree 0. Are we not allowed that? No. We are not allowed to have a degree 0 in the denominator, but in the numerator, nowhere anything was said about that. So it means this is a polynomial. So 2 is a polynomial, so this means this is a rational function. What about number 4? Yes, this is also a rational function because we have polynomial over a polynomial. Now what about last one? So it is 1 over x plus x, and the bottom is 2 minus 5 over x. So if you recall, we can easily write it and we can simplify, and this gives us 1 plus x square. I will leave it for you to check this basically, that the two are same. So, but this is rational. But what about the given one? So you say that this function is not rational. Okay, why? Because the top is not a polynomial and the denominator is not a polynomial as well. Now they can be converted into polynomials. This function can be converted into a rational function, but we are not going there. But at the first look after the function, we want to see whether it is rational or not. Okay, I will stop here and more in the next video.